Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the JK flip-flop. So similar to the SR flip-flop, this JK flip-flop also has two inputs. And using the two inputs, we can change the output state of the flip-flop. So it is very useful in the design of various counters. Now the behavior of the JK flip-flop is very similar to the SR flip-flop. That means when both inputs J and K are 0, then the flip-flop will retain its current state. And similarly, when this J is 0 and K is 1, then the flip-flop will get reset. Likewise, when the J is 1 and the K is 0, then similar to the SR flip-flop, the output of this JK flip-flop will become 1. But unlike the SR flip-flop, when its both inputs are 1, then its output will toggle. So in case of the SR flip-flop, we have seen that when its both inputs are 1, then its output is indeterminate. So behavior wise, that is the only difference between the SR and the JK flip-flop. So this is the symbol of the positive age triggered JK flip-flop. So this flip-flop will respond to the inputs only at the rising edge of the clock. Similarly, this is the symbol of the negative age triggered JK flip-flop. So as you can see, there is a small bubble over here, which indicates that the flip-flop will respond to the input only at the falling edge of the clock. So now, let us see the logic circuit of this JK flip-flop. So with the little modification in this SR flip-flop, it can be converted into the JK flip-flop. So here, this is the basic circuit of the SR flip-flop. So here, this box is the SR latch, and using the two more AND gates, it can be converted into the gated SR latch. So here, this input is the enable input. So if we directly apply the clock signal over here, then it will behave as the level triggered flip-flop. But as we have seen in the previous videos, using the pulse transition detection circuit, the same gated latch can be converted into the flip-flop. So with this additional circuit, this circuit will work as the SR flip-flop. So if we want to use the same circuit as the JK flip-flop, then here, in place of the R input, the K input is applied, and in place of the S input, this J input is applied. Moreover, here this Q output is connected back to the AND gate where this K input is applied, and similarly, this Q bar output is connected back to the AND gate where this J input is applied. So with this little modification, now the same circuit will work as the JK flip-flop. So let us see how. So here, when there is a no clock transition, then the output of both AND gates will be 0. That means in that case, both S and R inputs will be 0. And as you know, when both inputs of the SR latch are 0, then it will retain its current state. So in this case, when there is a no clock transition, then this JK flip-flop will retain its present state. Similarly, when both inputs are 0, then also the output of these two AND gates will be 0. And in that case, both S and R inputs are also 0. So in this condition also, the flip-flop will retain its present state. Likewise, when this J is 0 and K is 1, then at the clock transition, the output of this lower AND gate will be 0. But the output of this upper AND gate will depend on the value of the Q. So if this Q is 1, then the output of this AND gate will be also equal to 1. So in that case, if you see, then this R is 1 and S is 0. And therefore, this flip-flop will get reset to 0. That means in this condition, this Q output will be 0. On the other hand, initially if this Q is 0, then the same 0 will also appear over here. And in that case, the output of this AND gate will be equal to 0. So if this Q is 0, in that case, with K is 1 and J is 0, the output of these two AND gates will be 0, and in that case, the flip-flop will retain its current state. So as you can see, for the both possibilities of the Q output, when this J is 0 and K is 1, then the Q output will remain 0. Or in other words, the flip-flop will get reset to 0. Similarly, when this J is 1 and K is 0, then at the clock transition, the output of this upper AND gate will become 0. But this output of the lower AND gate will depend on the value of the Q bar. So if this Q bar is 0, or in other words, if this Q is 1, then this input will be equal to 0. And therefore, the output of this lower AND gate will also be equal to 0. So in this condition, if you see, then both inputs S and R is equal to 0. And therefore, the flip-flop will retain its present state. So in this condition, the current state is equal to 1. That means in the next state also, it will remain in the same state. On the other hand, currently, if this Q is 0, then this Q bar will be equal to 1. And the same 1 will also appear over here. So if this Q bar is 1, in that case, the output of this lower AND gate will become 1. That means in this condition, with the same inputs, this S is 1 and R is 0. So with these inputs, the flip-flop will get set to 1. That means in this condition, this Q output will become 1. So as you can see, irrespective of the present state of the flip-flop, when this J is 1 and K is 0, then the flip-flop will get set to 1. And likewise, let us see what happens when both inputs J and K are 1. So whenever both J and K inputs are 1, then at the clock transition, the output of these two AND gates will depend on the value of this Q and Q bar. So if this Q is 1, then this Q bar will be equal to 0. And the same outputs will also appear over here. So if this Q is 1 and this Q bar is 0, then the output of this upper AND gate will become 1. On the other end, the output of this lower AND gate will be equal to 0. So in this condition, if you see, then this S is 0 and R is 1, and therefore the flip-flop will get reset. That means in the next state, the output of the flip-flop will become 0. Similarly, let us take the another case where the value of Q is 0 and this Q bar is equal to 1. So if Q is 0 and Q bar is 1, then the output of this upper AND gate will become 0, while the output of the lower AND gate will become 1. So in the present state, if Q is 0 and Q bar is 1, then over here, this S is 1 and R is 0, and therefore this flip-flop will get set. So in short, we can say that when both inputs J and K are 1, then the output of the flip-flop will toggle. That means currently, if Q is 0, then in the next state, this Qn plus 1 will become 1. On the other hand, currently if Q is 1, then in the next state, this Qn plus 1 will become 0. So this is the truth table of the JK flip-flop. So similar to the SR flip-flop, this JK flip-flop can also be implemented using the NAND gates. So earlier we have seen that how to implement the gated SR latch using the NAND gates. Now in this circuit, when we connect this clock transition circuit to that enable input, then this gated latch will respond to the input only at the clock transition. And in this way, it will behave like the flip-flop. Now to use the same circuit as the JK flip-flop, the J input is applied in place of the S input, while the K input is applied in place of the R input. And as you can see, this Q bar output is connected to the NAND gate where this J input is applied, and similarly, this Q output is connected to the NAND gate where this K input is applied. So in this way, with the little modification, now the same circuit can be used as the JK flip-flop. So in short, this is the circuit of the JK flip-flop using the NAND gates. Alright, so now let us see the characteristic equation of this JK flip-flop. So as we have seen earlier, the characteristic equation is the output of the flip-flop in terms of the present state of the flip-flop as well as the current inputs. That means here we have the three variables, that is Qn, J and K. And for the three inputs, we have total 8 different combinations. So as we have seen, when both J and K inputs are 0, then the flip-flop will retain its current state. That means if this Qn is 0, then this Qn plus 1 will also remain 0. And if this Qn is 1, then this Qn plus 1 will be 1. Similarly, when this J is 0 and K is 1, then irrespective of the present state of the flip-flop, in the next state, it will reset to 0. Similarly, if this J is 1 and K is 0, then irrespective of the present state of the flip-flop, in the next state, the flip-flop will get set to 1. And likewise, when both J and K inputs are 1, then the output of the flip-flop will get toggle. That means currently, if this Qn is 0, then in the next state, this Qn plus 1 will become 1. On the other hand, if this Qn is 1, then in the next state, this Qn plus 1 will become 0. So as you can see, here this output Qn plus 1 is logic 1 for the 4 different input combinations. So let us mark all those minterms in the K map and let us try to simplify the Boolean expression. So here, this 100 corresponds to minterm M4, while this 010 corresponds to minterm M2. Likewise, this 110 is the M6, while this 011 corresponds to M3. So let us mark all those minterms in the K map. So here, after marking all the minterms in the K map, let us make the group of these minterms and let us try to find the simplified Boolean expression. So here, as you can see, we can make the group of this minterm M2 and M3. And likewise, we can also make the group of these two ones, that is the minterm M4 and M6. And just by making these two groups, we are able to cover all the ones in the K map. So here, this group corresponds to Qn bar dot J, while this group corresponds to Qn dot K bar. Because in this group, if you see, then the variable Qn is not changing and its value is equal to 0. Similarly, here this J variable is not changing and its value is equal to 1. Therefore, this group corresponds to Qn bar dot J. Likewise, in this group, if you see, then here the value of Qn is 1, while the value of this variable K is equal to 0. Therefore, this group corresponds to Qn dot K bar. So if you see the overall expression, then that is equal to this J dot Qn bar plus K bar dot Qn. So this is the characteristic equation of the JK flip-flop in terms of the present state as well as the current inputs. So similarly, now let us see the excitation table of this JK flip-flop. So as I said in the previous video, this excitation table shows the required inputs or the required excitations of the flip-flop to go from the current state of the flip-flop to the next particular state. So let's say currently this Qn is equal to 0, and in the next state we also want this Qn plus 1 to be equal to 0. So for this transition to occur, let us see the required excitations of the inputs J and K. And to find that, let us take the help of the truth table. So here, for these two input conditions if you see, then this Qn plus 1 is equal to 0. So here, when this Qn is 0 and both J and K inputs are 0, then in the next state, this Qn plus 1 will also remain 0. Secondly, when this J is 0 and K is 1, then also this Qn plus 1 will remain 0, because in this condition, the flip-flop will get reset. So as you can see, for this transition to occur, the value of variable J should be equal to 0, while the value of variable K can be either 0 or 1. That means we can write it as J is equal to 0 and K is equal to X, where this X indicates that the value of K can be either 0 or 1. Similarly, let us take the second case. So in this case, currently this Qn is 1 and in the next state, we want this Qn plus 1 to be equal to 0. So for these two input combinations if you see, then in the next state, this Qn plus 1 is equal to 0. So as you know, when this J input is 0 and K is 1, then irrespective of the present state of the flip-flop will get reset. That means currently, if this Qn is 1, then in the next state, this Qn plus 1 will be equal to 0. Secondly, both J and K inputs are 1, then the output of the flip-flop will get toggle. That means currently, if this Qn is 1, then in the next state, this Qn plus 1 will become 0. That means for these two input combinations, we will get our desired transition. So for this transition to occur, the value of variable J can be either 0 or 1, while the value of variable K should be equal to 1. So we can write it as J as X and K as 1. So that is the required excitation for the given transition. Similarly, let us take the third case, where currently this Qn is 0 and in the next state this Qn plus 1 is equal to 1. So this transition will occur for these two input combinations. So as you can see, when this J is 1 and K is 0, then irrespective of the present state of the flip-flop, in the next state, the flip-flop will get set to 1. That means this Qn plus 1 will become 1. Similarly, when both J and K inputs are 1, then the output of the flip-flop will toggle. That means currently, if this Qn is 0, then in the next state, it will become 1. That means for this transition to occur, the value of input J should be equal to 1, while the value of input K can be either 0 or 1. So we can write it as J is equal to 1 and K is equal to X. So that is the required input combination for the given transition. Similarly, let us take the last case. So in this condition, Qn is currently 1, and in the next state also, we want this Qn plus 1 to be equal to 1. So it will occur for these two input combinations. So as you can see, when both J and K inputs are 0, then the flip-flop will retain its current state. That means currently, if this Qn is 1, then in the next state also it will remain 1. And the second case is when this J is 1 and K is 0. So as you know, when this J is 1 and K is 0, then irrespective of the present state of the flip-flop, in the next state, the output will become 1. So currently, if this Qn is 1, then in the next state, it will remain 1. That means for this transition to occur, the value of variable J can be either 0 or 1, while the value of variable K should be equal to 0. So we can write it as J is equal to X and K is equal to 0. So this is the excitation table of the JK flip-flop. And in this way, we can write the excitation table of the any flip-flop. So now, using the timing diagram, let us see when both J and K inputs are changing with the time, then how this JK flip-flop will behave. And here, let us assume that the flip-flop is the positive edge triggered flip-flop. So at the first rising edge, if you see, then here this J is 0 and K is equal to 1. Therefore, the output of the flip-flop will become 0. So here initially the output is already equal to 0. So it will remain in the same state until the next rising edge. So now at the next rising edge, if you see, then now this J is equal to 1 while the K is equal to 0. And therefore at the next rising edge, this Q output will become 1. And it will remain in the same state until the next rising edge. That means up to this point, this Q output will remain 1. Now at the next rising edge, if you see, then now both J and K inputs are 1. And therefore, the output of the flip-flop will toggle. That means currently, since Q is 1, so in the next state, it will become 0. And it will remain in the same state until the next rising edge. So this is the overall output of this JK flip-flop. And if you see this Q bar output, then that is exactly opposite to the Q output. Now if this flip-flop is designed using the gated latch along with the clock transition circuit, then at every clock transition, this clock transition circuit will generate the narrow pulses. And due to that, this latch will get enabled only for the very small duration. Typically, this duration is in the nanoseconds. But if these pulses are not narrow, and if it is much larger than the propagation delay of the flip-flop, or secondly, if this flip-flop is the level triggered, then the race around condition may occur in this JK flip-flop. So let us see this race around condition in this JK flip-flop, considering that it is the level triggered. So if you see this circuit, then this is basically the gated latch. And here, this clock signal is directly applied to this enable input. So in this condition, this gated latch will behave as the level triggered flip-flop. So now, the same inputs J and K are applied to this flip-flop. So now whenever this clock signal is high, then initially this J is 0 and K is 1. That means initially up to this time, the output of the flip-flop will remain 0. Now over here, this J input becomes 1. And since the clock signal is still high, so the output of the flip-flop will also become high. Because in this condition, since both J and K are 1, so the output of the flip-flop will toggle. And because of that, it will become high. Now if you see over here, then only during this time, both J and K inputs are high as well as the clock signal is also high. Let's say this time is equal to 1 microsecond. But if we compare this time with the propagation delay of the flip-flop, then this time is much larger than the typical propagation delay of the flip-flop. So let us just zoom this portion and let us see what is the output of the level triggered flip-flop when both J and K inputs are high and the clock signal is also high. So since it is a level triggered flip-flop, so during this entire 1 microsecond, this clock signal will remain high. And at the same time, here both J and K inputs are also high. So as you know, when both J and K inputs are high, then the output of the flip-flop will toggle. So initially, since this Q is 0, so in the next state, it will become 1. So here, let's say the propagation delay of this logic gates is equal to 20 nanoseconds. That means just after 40 nanoseconds, for the given inputs, the output of the flip-flop will toggle. And now it will become 1. So after 40 nanosecond, the same 1 will also appear over here. And similarly, this Q bar will also appear over here. Now here, since the clock is still high and both inputs are also high, so once again, this flip-flop will become transparent and it will respond to these new inputs. So now if you see, then this R input will become 1, while this S input will become 0. And because of that, once again, the output of the flip-flop will become 0. That means now this Q will become 0 and this Q bar will become 1. And it will happen only just after the 40 nanosecond. Now once again, this 0 will appear over here, while this 1 will also appear over here. And still both inputs and the clock signals are high. So once again the flip-flop will respond to the new inputs. That means once again, now this output will become 0, while this output of the AND gate will become 1. That means now this S is 1 and R is 0. That means once again the flip-flop will change its state from 0 to 1. So as you can see, the output of the flip-flop is continuously toggling between the 0 and 1. That means if the JK flip-flop is level triggered and its both inputs are high, then during the on time of the clock, the output of the flip-flop will toggle continuously between the 0 and 1. And this condition is known as the race around condition in this JK flip-flop. So this condition can be avoided if the flip-flop is the age triggered and the pulse which is generated by this clock transition circuit is very narrow. That means using the age triggered flip-flop, we can avoid this race around condition. So that is all about the JK flip-flop. So I hope in this video you understood the working of this JK flip-flop and you also understood how to write the characteristic equation as well as the excitation table of this JK flip-flop. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.